speaker today is Marco Colombo. Marco is a senior research fellow at the University of Leeds. He joined the University of Leeds in 2013 after obtaining his PhD from the Polytechnic University of Milan. His main research interests are in the modeling of multiphase gas-liquid flow, boiling, heat transfer, natural convection, turbulent fluids, and nuclear thermal hydraulics, and different levels of complexity and scale resolution. Today, he will talk about computational modeling of multiphase gas-liquid fluids and different scale resolution. Hi, Marco, I hand it over to you.
Thank you very much for the kind introduction. Let me. Can you see my screen well?
Yeah.
Perfect. No, I'm just okay. So thank you very much for the kind introduction. In my talk today, I want to provide an overview on the research ongoing at Leeds on the development of computational models that can be applied to all flow regimes in multiphase gas-liquid flows. So we can find multiphase flows essentially everywhere in any engineering or industrial application. They can provide good mixing properties, allow high heated mass transfer rates due to the large interfacial area that they can provide for this transfer to occur. But at the same time, the presence of that interface is also a big challenge, because we can find different flow regimes as a function of the phase pattern, of the phase distribution patterns. And in these, we can have interfacial scales that span over very large range of length scales. And for this reason, even if we now use computational models extensively to model multiphase flows, the modeling of this interface, of the interfacial physics, and of the multi-scale features of these interfacial physics is still a big challenge for the computational models available. Normally, all the flow regime can be distinguished between dispersed regime, such as small bubbles dispersed in a continuous liquid or small droplets dispersed in a continuous gas, and also segregated regimes or large interfaces regimes, such as slugs or plugs of gas in liquid, or also stratified flows where two fluids with different density flows in a stratified pattern. So essentially, nuclear thermal hydraulics, we probably can find all of these flow regimes. And the additional problem is that most of the time we don't have very well-defined condition, but we have a mix of dispersed and large interfaces that coexist in the same flow. And the other problem is that we have computational models, yes, and they have been successful, and that's another yes, but most of the time that they have been successful on only specific flow regime, on a few number of those, and when conditions are well specified, for example, for bubbly flows. And so, considering this, there is a great benefits that we can have if we are able to develop an all flow regime computational model. So a model that can be applied irrespective of the specific flow regime that occur, and that can provide enormous benefit to the modeling of boiling in nuclear thermal hydraulics, and also in nuclear thermal hydraulics to the modeling of different scenarios that occur during loss of coolant accident. And so this is essentially the main aim of the research, try to develop a model that is applicable to all flow regimes. So this has been already addressed in previous presentations. So what are the most used modeling techniques? We have the multi-fluid model, where the instantaneous field is essentially averaged. So in this case, we have bubble dispersed in a liquid. after the averaging, we don't have the bubble anymore. We have what is called interpenetrating continua model. So the two phases become both continuous in the computational domain. And what we know is the amount of gas and the amount of liquid that we have in each cell. So the volume fraction of each phase in each cell. We don't have the interface anymore, and all the interfacial transfer processes have to be modeled. The advantage of this model is that it's quite robust and can be applied even to large scale flows and complex geometry, and has been successful in some flow regime. For example, there have been reported very good prediction or good prediction of, for example, bubbly flows, in particular because that can be characterized by the flow of an averaged bubble. But the downside of it is that it's an average model, so we don't have the interface anymore, is subjected to diffusion, and is essentially, because of the average treatment, unable to capture large intermittent structures that are common in large interface regimes, for example, a slug flow. On the other side, we have interface resolving method that have been described very well in the first presentation today. In these, all the details of the interface and the flow are resolved. So in theory, they can be equipped to resolve any flow regime, but the issue with those models is the computational resources that are required to resolve all the flow and interface details. So our strategy here is to overcome the limitation of the two models. Is essentially summarized in the model we are developing, which is called Generalized Multi-Fluid Modeling Approach, or GEMMA is the acronym. Essentially, what the model wants to do is introduce in the multi-fluid modeling framework some kind of interface resolving capabilities in a multi-fluid sense. So it's based on the multi-fluid solver reacting Euler form or open form, and includes different features. One is a compression term, which is this one that is added to the continuity equation, and that is essentially a numerical feature that counteracts the diffusion that normally affects multi-fluid models. And it is essentially based on this compression velocity that is obtained from the normal to the interface and the relative velocity. So this is a compression velocity that will act normal to the interface, and also will be modulated by the relative velocity and will maintain the interface sharp, and it will be active only when large interfaces are present. And this is achieved by this scalar field C alpha, which is 1 when a large interface is present, and 0 where instead the flow regime is dispersed. Now, since we have that, how we are able to detect if a large interface is present in our multi-fluid field? Well, the model does that in two ways. One is based essentially on the mesh resolution, by defining this local interface resolution quality parameter, and that is essentially quantifies how well we are able to resolve the interface on the computational grid. You see an example here. Higher values of that ERQ means higher resolution. So this is, for this small bubble is 1, so probably, I mean, we are not able to capture that. This is 2, for this is 4, so we may try to capture this interface and also this large interface down here. And the other parameter that is used is the local size of the dispersed phase that is normally provided by a population balance. So when the local size of the dispersed field is higher of a certain value, then the large interface model does that. And essentially that C alpha field turns to 1, and it means in that region there is a large interface. So the last step is, since we are still in a multi-fluid framework, is to identify the correct closure relation that we want, because The interface is detected, is kept sharp, but still we have to rely on interfacial closure. And what the model does is selecting the most proper one for the regime that is found there. And we do that by building on top of the blending already available in OpenFOAM. And essentially, let's show how this works. So focusing on the interfacial momentum transfer. Interfacial momentum transfer is modeled by a sum of forces. We have drag, lift, wall, turbulent dispersion, virtual mass, and surface tension. In dispersed regime, we have all of these active except for surface tension. Instead, in large interfaces, we only have drag and surface tension. So the formulation for drag for all the flow regime is this. So essentially, when C alpha is 1, so a large interface is present, the large interface drag is used. Instead, when it's 0, a combination of the gas in liquid drag model with the liquid in gas drag model is used, depending on the volume fraction there. Surface tension is modeled in this way, so it's active only where C alpha is 1, so large interface is present. And instead, all the other forces that are only active in dispersed regime are modeled in this way. So gas in liquid and liquid in gas, and 0 when a large interface is present. And in this way, we achieve a blending of the interfacial closure that really depends on the local interface morphology and is not dependent of predetermined map of the volume fraction as it is already done in some other available models. So I just maybe want to provide an example of how this works by providing one validation case that we have done on a rising bubble in liquid at rest. You see the bubble here starts spherical, that rises in liquid and assumes an ellipsoidal shape. And this is the C alpha field. You see that is 1 essentially on the interface of that bubble. And so it means that the model detects that this is a large interface and it has to use the large interface model in this area. And you see here to plot for the average rising velocity of the bubble and the average height in the liquid. And it's the black line, our model. The square and the red line are results for interface tracking simulation. And you see the results are quite good where compared to interface resolving techniques. And instead, this is the opposite. So a dispersed regime, a bubbly flow, low void fraction, 3–5%. In this case, the interfacial momentum closure is this one. We have drag, lift, wall, turbulent dispersion, and virtual mass, so no surface tension, and the dispersed regime drag active. And in this case, the large interface regime does not activate. You see that this is the results of the volume fraction distribution. We have a dispersed field, and this is instead a radial profile in this direction of the void that peaks at the wall. There are probably some improvement that can be done still on the closures employed, but the main features of the flow are predicted. And the main point here is that in this case, the interface compression is not active and the model works fine in the dispersed mode. We have other additional validation cases that can be found in this paper recently published, but I want to use the remaining time today to present 2 cases that are more related to nuclear thermal hydraulics. And one is a stratified flow, which is important for some phenomena such as pressurized thermal shock and countercurrent flow limitation, and also important in the oil and gas field for the formation of slugs. So we have applied the model to the stratified channel flow investigated by Fabre et al. Is a horizontal channel with water on the bottom and air flowing on top. And what has been observed is a smooth stratified flow that becomes wavy and perturbed when the flow rates of the 2 fluids are increased. So this case has been used mainly to assess the behavior of the turbulence model. So in general, since the model is implemented the general way in OpenFOAM, it can work with any model. included. We use here a mixture K epsilon model, and the reason is that, okay, if we go back, or we can have a, no, let's go back. So if we have a turbulence model for each phase, we will have to solve, since it's a multi-fluid model, the turbulence model for air example also in the water phase, where air is negligible. And that can cause numerical instabilities. In this way, instead, we are able to put everything in the mixture, and that allows us to simulate the turbulence model, the turbulence there quite well, recovering the behavior of each single phase in the respective region. So we have a, similar to the interfacial momentum closure, we have a closure for the a model for the interfacial turbulence as well. This is and that includes bubble-induced turbulence at the present time, not used in this case, and also this additional term here, which is a suppression of the turbulence near the large interface, which is a common problem in multi-fluid models and allows to avoid very large unphysical value of the turbulence near the interface. And these are instead some results. You have the volume fraction distribution. There you see air flows on top. The liquid height is quite well predicted, even if we have still some distance from the experimental measurement. And these are velocity profile in the vertical direction, and also turbulence kinetic energy. And you see, if we don't account for the suppression, how high is the turbulence kinetic energy there. And this does not allow to correctly predict the velocity profile, because we have a strong peak near the top because of the large interfacial shear that is predicted in this case. Instead, when turbulence suppression is active, we have a good prediction of the kinetic energy in the channel, and also a good prediction of the velocity profile. The model works essentially in the large interface regime. The interface is not diffuse, and the smooth stratified flow is well predicted. A similar, I just want to show other results from a similar case. This is a slug flow in an annular channel that has been studied here experimentally in Norway, and also in this paper here with the volume of fluid. And essentially, it involves the formation of liquid slug along the annular channel. And this is instead our simulation with our model. And you see clearly the time rate is different, but you see the slug developing and going along the channel as a function of time. And you see here the average void in the channel and the passage of multiple slugs in the entire transient. And preliminary result shows that we are in principle able to predict the frequency there. And the main advantage with our approach will be to perhaps use less refined meshes, and also be able to more properly model the dispersed part of the domain that are found between slugs. Last results I want to show is for flow regime transition, which instead is more proper in nuclear thermal hydraulics for the modeling of flow boiling, and so of the entire boiling channel. And in particular of this experiment here in an horizontal pipe, where the flow rate has been changed to obtain the different flow regimes. So we have bubbly flow, the formation of plug, and then the formation of slugs in the pipe. And in this case, what we have is that the model is coupled with the population balance model based on the class method, and is the model already available in open form. So essentially, in the bubbly flow, the model correctly works in the dispersed regime. You see here a distribution of the void fraction. This is the bottom of the pipe. This is the top. Bubbles accumulate on the top, but the model still operates in the dispersed regime. Then, if we increase the void fraction, we go to what is called stratified bubbly flow here. This is an image from the top of the channel. And you see that the void diffraction here becomes quite high, perhaps is close to 0.6, but still the model predicts the dispersed regime. If we increase the gas flow rate even more, the diameter will become higher than 6 millimeter due to coalescence, and plug and slugs starts to form. Yeah, I have an animation of that and show the simulation of the two regimes, the plug regime and the slug regime here. You see that with the time, this large vapor structure starts to form. The formation of large interfaces are detected. This is an example of the C alpha field. For the plug case, you see that how is 1 in the location of the large interface. And here instead, this is the diameter for the plug flow. You see that is below 6 between the gas plugs and is higher than 6 in the gas plugs. That's not important because there is no coalescence happening there since we have continuous gas. And if we increase the gas even more, the model turns to perfectly stratified flows, as in this case here. So, and the important things to note is that we start from the same uniform initial condition, and this is quite a good result that the model is able to develop in the different flow regime, starting from the same initial condition with a uniform bubble distribution having diameter of 1 meter, as in the experiment. So yeah, this was the main features of our generalized multifluid modeling approach. The most important characteristic are that it recognizes the interface morphology from the local conditions, so does not need any a priori map of volume fraction, and also will allow us to selectively decide which scale of the interface we want to resolve. I've shown different application, different example. I want to say last few words on the future development. In the last example of the pipe, I've shown the transition from dispersed to continuous. Work in the future we need to address the transition from continuous to dispersed, which mean entrainment and deposition for the stratified case, and also the breakup and shearing off of small bubbles from the large plug and slug that we've seen in the pipe. And also the extension of the model to additional physics include at the interface heat and mass transfer, and the work of mass transfer, in particular regarding liquid-liquid extraction, is already ongoing at the University of Leeds. So with this, I want to thank the EPSSC for the financial support, my colleagues that are working with me in the development of this model, and you all for the attention, and I'm happy to answer any question that you have.
Thank you, Marco. Very impressive talk. Any questions?
Let me...
Yeah, could I butt in? Mike Block, Imperial College again. You had this parameter gamma that
yes
selected the determined whether, as I understood it, the choice to treat it one way or another. How sensitive is it to the choice of that?
Well, it's completely sensitive in the sense that, I mean, this gamma means, let me go back. Can you still see the screen?
Yeah.
Okay, so essentially it says that we want to resolve that interface when it's higher than the mesh size by at least gamma. So if we say gamma is 1, of course, that will be an interface that is the same size of the mesh, so we won't be able to resolve that. So that is critical and is completely dependent on that selection. But at the same time, it allows us to say, well, we are not interested in solving 4 millimeter bubbles because we can characterize them well with the dispersed mode, but we are interested only in resolve much larger, much bigger bubble that we struggle to characterize with the dispersed mode.
Sure. Okay.
But it's a parameter that is completely the choice of. Yeah, you can fix it in the simulation setup.
And one other thing, you used K-epsilon model in a later example.
Yes.
Have you tried it with other turbulence models? Is it easy to?
Yes, not in that particular case, even though I have some LES currently.
Yeah, not so much in that, but if it was, for instance, a valve or a pump or something, and you had, K-epsilon models aren't great.
Yeah, well, it's immediately compatible with the Reynolds stress, for example. Ideally, with all the models in OpenFOAM, that is not. I'm not saying that you switch the model, it works, because any model
but in
will
principle,
probably.
It's easy to implement.
Yes. It will work. Then maybe the model will require additional modeling improvement to work with this particular framework.
Okay, thank you.
Any more questions for Marco?
Maybe I will.
Hi, it's Susan here. Thanks again, Michael. That was quite quite an interesting talk. And following on the questions from Mike about the Thomas modeling, I'm thinking actually the opposite of this. That is because the flow is so strongly influenced by the two-phase interface and everything else. I wonder whether sophisticated, more complicated models would be able to help at all. If you think about the detailed velocity gradient here, field and all that, I presume you won't be able to resolve in many cases. As you say, you only you have to probably choose to some size bubbles and everything. So but overall, it's actually interesting modeling. I'm wondering whether you could actually go even the other way, like using simpler models, like a mixing lens, and because that way, because the main flow field for one phase probably is not closely resolved, and the complex kind of terms in the turbulence models, the production and dissipation are strongly dependent on the accurate resolution of the velocity field, which I presume you won't be able to achieve.
Yes, I'm not sure. I'm not sure I've understood entirely the question.
It's basically what I'm trying to say is we actually have two-phase flow, strong interface, the whatever velocity field you resolve will be interesting, but close to the interface there will be like a velocity gradient you probably won't be able to resolve, and also close to the wall, and those gradients may play an important role in turbulence modeling. To me, this unless you go for like the first speaker, as you go to RES, in which case you actually resolve the flow in detail, then you may have to ignore the local velocity gradients, in which case I mean, I know you have done significant expression as you mentioned, and that really changed the turbulence, whatever turbulence you use already, and any improvement on turbulence modeling, so-called improvement on turbulence modeling, may not really help a lot. I suppose that's what.
Yes, well, yes, that will be that is for sure right. I mean, it's still it's actually an incomplete resolution, and in fact, what you say is completely true. I mean, in this case, in the case I've shown, we have a flat interface, but if you have waves on that or perturbation of that interface, is correct. You won't be able to capture the turbulence, or you won't be able to resolve the turbulence completely, the turbulence that is generated by those. So you will have to account for additional models of the turbulence generation by those perturbation. And even in LES, there is literature evidence that you need, if you're using a multi-fluid model, include some kind of suppression modeling, because the resolution of that area is incomplete. It's not that is resolved as in a one fluid model where all the scales are resolved. But at the same time, you are able to select the closure more properly and use the right one where you need them and where they are more useful.
Any more questions for Marco? All right, shall we go to our last section, is general discussion. This discussion is welcome anyone want to share his or her opinions on the multiphase flow or the boiling. Or any questions for previous speakers, both are welcome. Quite quiet.
Well, it may help if you stop sharing. I presume that probably would help, so everyone can see themselves, and then they would have to speak. Like I've seen now, Michael is active. So I mean, for me, I think today's talk is really interesting in the sense that I know even for single phase flow, we were able to resolve everything. It's actually quite difficult, but now look at what has been done in two-phase flow. They are overtaking simulations of single phase. I'm wondering whether, in any case, whether even if you go for DNS, there will be a lot of modeling involved. And they have to increase around us, even for the kind of the same global configurations, conditions, the flow behavior can still be very different for different surface conditions, or how long the same test has been running, for how many hours as a result, the surface conditions have changed, and then everything else probably have changed a lot, which means whatever you do, you still have to include a lot like calibration or modeling in it. Does that make sense?
Yeah. Another point we have not yet talked today is about the high performance computing, the performance of the code when you apply them to the multi-phase flow, because in multi-phase flow, you may need very fine mesh, high mesh resolution to capture the interface or small computation phenomena that will increase a big mesh, or they ask for lots of computational calls that also increase the requirement for your code to have a very good scaling performance.
So you for instance, you mentioned that you had you had to use a lot of resources. So what was the number of processors you were using
So
for the larger simulation, let's say?
so let's say, yeah, I use only CPU. I mean, not GPU.
Okay.
Yeah, because our code is parallelized with the domain decomposition using MPI.
Mm-hmm.
And yeah, I actually don't plan to parallelize the current code to GPU, because if it's explicit method, and then it makes sense to parallelize with GPU. But if we use an implicit method, it may improve the speed twice or 3 times. But actually, it's not what I want to do. And actually, the changing code to GPU is just introduce more complicated situation. And actually, the student cannot develop the code or modify the code easily. So I plan to stick to CPU parallelization. But usually I use, let's say, 500 or 256 cores.
Okay, thank you very much.
Yeah, it's interesting that the kind of computation power required for two-phase flow is actually quite similar to single phase. And I remember you said your mesh is about 30 million, which is a typical mesh we use for single phase flow at low Reynolds number flow. And I'm wondering whether in terms of the scales, the spatial scales, time scales, the two-phase does not actually increase the scales much, which means the mesh you use for single-phase flow should be able to actually resolve two-phase flow if the scales are not significantly shortened in the two-phase flow.
Well, I think you're using quite fine mesh because I guess you're talking about DNS. But in my case, I'm doing LES. And the grid scale is like 100 microns, and the time scale is like time step is about 1 microsecond. And the duration of my simulation is, let's say, 1 or 2 seconds, a few seconds. So my simulation is usually 1 million or 2 million time steps. So yeah, of course, I want to use more finer mesh, but it really depends on the resources I can use. And actually, the speed of CPU doesn't stop. I mean, it continues to increases, even though the CPU clock doesn't improve so much, but the speed of calculation is increasing. So I still expect the advance of hardware.
Thank you.
Okay, yeah, it's 4 o'clock. Shall we stop here? And thank you very much, everyone. Thank you for joining us in the seminar. And thanks for all the speakers. They are very good talks. Thank you.
Thank you very much.
Thank you, everyone.
Bye.
Thank you,
Thank
everyone.
you.
Thank you. Bye.
Bye.